July 12 through 16, 1995, Chicago. A high-pressure system stalled over the upper Midwest, suppressing atmospheric circulation and trapping radiative heat within the urban boundary layer. Overnight temperatures failed to fall below 80 degrees Fahrenheit on multiple consecutive nights. The city's thermal environment did not reset. Systems designed around daily cooling cycles operated without recovery intervals for 5 consecutive days. Chicago's summer climate is defined by humid continental conditions, with July averaging a daily high near 84 degrees Fahrenheit and overnight lows typically falling to 68 to 70 degrees Fahrenheit. This diurnal temperature swing of approximately 14 to 16 degrees Fahrenheit forms the operational baseline for the city's infrastructure. Residential construction, electrical load forecasting, and public service scheduling are calibrated against this recovery window. Masonry and concrete structures in dense residential zones absorb solar radiation during daytime hours and dissipate stored heat during overnight periods. When overnight lows remain above 80 degrees Fahrenheit, this dissipation cycle is interrupted. Buildings retain thermal load into successive days, compounding interior temperatures. Chicago's cooling infrastructure, mechanical systems, public facilities, and emergency response capacity was engineered around the assumption that nighttime temperatures would provide a consistent thermal buffer. The 1995 event invalidated that assumption across 5 consecutive nights. Beginning July 11, 1995, a dominant high-pressure ridge established itself over the central United States and remained stationary through July 16. Subsidence associated with the system suppressed vertical atmospheric mixing, preventing convective relief and reducing cloud formation. The blocking pattern deflected frontal systems that would ordinarily introduce cooler air from the northwest. Surface winds weakened significantly, eliminating advective cooling across the metropolitan area. The atmosphere above Chicago remained dry and stable at altitude, while surface humidity increased due to regional soil moisture and Lake Michigan proximity. This combination, subsidence aloft, surface moisture retention, and minimal wind, created conditions in which solar energy accumulated in urban surfaces without nighttime dispersal. The ridge did not break until a cold front arrived on July 16, by which point cumulative thermal exposure had persisted for approximately 96 to 120 hours across the metropolitan region. O'Hare International Airport recorded a peak temperature of 106 degrees Fahrenheit on July 13, 1995, establishing a new all-time high for the station. Midway Airport recorded 102 degrees Fahrenheit the same day. Heat index values, combining air temperature with relative humidity, reached 119 to 125 degrees Fahrenheit at peak afternoon hours. The National Weather Service issued an excessive heat warning, though formal heat emergency protocols were not uniformly activated across city agencies at the event's outset. Surface temperatures on asphalt and rooftop membranes exceeded air temperatures by 30 to 40 degrees Fahrenheit, reaching estimated values of 130 to 150 degrees Fahrenheit on exposed surfaces. Dew points remained elevated, ranging from 75 degrees Fahrenheit to 80 degrees Fahrenheit during peak days, preventing evaporative cooling from providing meaningful relief. The combination of high dry bulb temperature and sustained dew point elevation produced a heat index that exceeded human thermoregulatory thresholds during both daytime and nighttime hours simultaneously, and atypical of standard summer heat events in the region. Under antecedent dry conditions, natural infiltration within the Black Hills watershed can absorb a portion of incoming precipitation, slowing the conversion of rainfall to surface runoff. On June 9, 1972, rainfall rates surpassed infiltration capacity within the first hour of intense precipitation. Soil moisture storage was exhausted across contributing subbasins, and the shallow, rocky soils characteristic of the Black Hills terrain provided minimal additional buffering. As infiltration approached zero, the rainfall-to-runoff conversion ratio approached 1-to-1 across large portions of the upper basin. Overland flow times decreased sharply as sheet flow transitioned to concentrated channel flow across slopes. Tributary streams, including Rapid Creek's upper forks, began rising at rates measured in feet per hour rather than the feet per day typical of regional spring snowmelt events. The effective time of concentration for the watershed collapsed, delivering runoff volumes to the urban channel network within a compressed time frame that precluded staged drainage response. As Rapid Creek enters Rapid City from the west, its natural floodplain had been progressively encroached upon by urban development through the mid-20th century. Channel cross-sections in the urbanized reach were constrained by road embankments, bridge abutments, residential fill, and commercial construction that reduced the effective conveyance width below natural bankful geometry. Culverts and bridge openings presented discrete hydraulic constrictions, where flow capacity was fixed by structure dimensions rather than by channel width. In several locations, the constructed channel cross-section was capable of conveying flows well below the discharge arriving on the night of June 9th. These bottleneck points created backwater effects, causing water surface elevations upstream of each constriction to rise above bank level before peak discharge had arrived. The sequential hydraulic choking of the corridor meant that overbank flow began hours before the hydrograph reached its maximum, spreading water laterally into developed areas before infrastructure failure was complete. Stage records and post-event survey data indicated that Rapid Creek rose from near-normal levels to major flood stage within approximately 2 hours at multiple points in the urban reach. At Canyon Lake, a reservoir immediately west of the city, water surface elevation rose rapidly as inflow volumes exceeded the outlet structure's conveyance capacity. The dam impounding Canyon Lake was overtopped during the night of June 9th, and the structure failed, releasing stored water and contributing an additional surge to the downstream channel. Following dam failure, stage rise in the lower urban corridor accelerated beyond rates attributable to direct tributary inflow alone. Cross-section surveys conducted after the event documented high water marks indicating peak stages 10 to 20 feet above pre-flood channel bed elevations in portions of the urban reach. These stage values placed water surface elevations well above the ground floor elevation of structures built on the adjacent floodplain. Bridge structures across Rapid Creek and its tributaries in Rapid City were subjected to hydraulic forces exceeding their design parameters during the peak flow period. Rising water levels submerged bridge decks at multiple crossings, transitioning flow conditions from open channel to pressure flow through bridge openings. Pressure flow generates uplift forces and increased drag on deck elements, and also traps floating debris against upstream faces of bridges, further reducing effective opening area and increasing upstream stage. Several bridge structures failed structurally during the night of June 9, with deck sections displaced or destroyed. Roadway embankments at low points in the street network were overtopped and eroded, severing surface transportation links across the flooded corridor. The loss of bridge crossings eliminated lateral connectivity across the creek alignment, fragmenting the urban grid into isolated sectors. Access routes into and out of the most severely affected areas were rendered impassable by a combination of deep water, debris accumulation, and structural failure of crossing infrastructure. Rapid City's utility infrastructure sustained significant disruption during and following the flood. Electrical distribution equipment in low-lying areas of the creek corridor was inundated, requiring de-energization of circuits serving affected districts to prevent electrocution hazard in floodwaters. Utility poles and underground conduit runs crossing or paralleling the creek alignment were damaged by hydraulic scour and debris transport. The municipal water system experienced pressure loss and contamination risk as floodwaters infiltrated distribution infrastructure. Wastewater collection lines were overwhelmed by inflow and infiltration, and treatment capacity was exceeded during peak flow conditions. Natural gas service was interrupted in portions of the flooded zone where meter sets and service lines were submerged or structurally compromised. Restoration of utility services required physical inspection of each affected segment before re-energization or repressurization, extending the period during which impacted areas remained without basic services. Peak flooding on Rapid Creek occurred between approximately 10 p.m. on June 9 and 2 a.m. on June 10, 1972. Darkness eliminated visual assessment of water extent, depth, and current velocity across the flooded corridor. Emergency response personnel and equipment were unable to operate in moving water without direct visual confirmation of channel margins, submerged obstacles, and structural integrity of crossing points. Road closures implemented during the event were based on incomplete real-time information about which segments remained passable. Communication infrastructure serving portions of the affected area was disrupted, limiting coordination between response units and central dispatch. Aerial reconnaissance was not feasible at night under the precipitation and cloud cover conditions present. The combination of darkness, disrupted communications, destroyed crossings, and continuing rainfall confined initial response to perimeter operations. Systematic assessment of damage extent and conditions within the flooded zone did not begin until daylight hours on June 10. Post-event analysis by the National Weather Service and U.S. Geological Survey established the 1972 Black Hills flood as the most significant flash flood event in South Dakota recorded history at the time of occurrence. Official rainfall totals placed maximum basin accumulations between 10 and 15 inches over the 6-hour storm window, with point maxima exceeding values associated with any recurrence interval in regional frequency analyses. USGS stream gauge records and post-flood high watermark surveys documented peak discharges on Rapid Creek that exceeded the estimated 100-year flood level by a factor of several times at multiple cross-sections. The event was formally classified as a probable maximum flood approximation for the affected watershed segments. Federal and state after-action reports identified the combination of training convective precipitation, canyon topography, urban channel constriction, and canyon lake dam failure as the compound causative factors. The event subsequently informed revisions to floodplain delineation standards and infrastructure design criteria in the Black Hills region.